All right, so for today, this is looking back at some of the things in chapter 4 before we hit chapter 5 on our next class. Then looking ahead, too, we've got the first exam coming up. The next time we get together, I will do, I'll have an example problem that I'll do as a test-like question that I'll have you complete, and then I'll talk through how I do grading. If you've had me before, you know it's different. For those of you who haven't, you'll be very confused, and then you'll be okay after a little while. But for now, today we're talking about experimental versus theoretical distributions. So we've already talked about the binomial, the geometric, the hypergeometric, and the Poisson in terms of them being theoreticals. Today we're going to then link it to then experimental. So what you started with was this. So the experimental probability of picking a diamond from a deck, you should all know this because we've done a deck of cards now. What's the theoretical probability of picking a heart from a deck? 1/4. Or 50 seconds, because there's 13 diamonds in there. All right, so what we did today, and what several of you did, you shuffled a deck of cards, you picked one card from it, and you made note of whether it was a diamond or not. Then you put it back in and reshuffled, and that's what some of you did. For those that were below, we said 8 and below, so below 9, which is why it says for groups below 9. Then in those 10, you recorded the number of diamonds, and then you repeated that 10-card sampling a total of 10 times. So as someone said, that meant you shuffled well 100 times because you're doing a card and then shuffle, 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 and then a card and then shuffle, shuffle, shuffle. So you are shuffling well every card, and if you're doing 10 cards and then 10 sets, you've shuffled at least 100 times. All right, then you record the frequencies in the table, and we combined all the groups, which is over there on the left. And this last one, it says combine all groups, and then theoretically, I'm telling you that this is approximately a binomial distribution. How do I know it's a binomial distribution? Binomial distribution, the conditions are, and these are the things that you need to be able to recall. 1, there are only 2 outcomes. You either had a diamond or it was not a diamond. Don't say it could be a diamond, heart, club, or spade. That's not correct. It's either a diamond or not a diamond. So the outcome was a buy in terms of there's only 2 possibilities. Okay. Second thing, the probabilities are independent and constant. So the likelihood of picking a diamond on every draw of your card deck is 1/4 because you replace it, reshuffle it really well, the probability is constant. There are a fixed number of trials. We're doing 10. You do it 10 times, then you count how many diamonds, and then we're seeing how many total successes we have. That's a binomial. And the way that would be noted is there are samples of size 10, and the probability of success is 1/4. So my x, my variable x, will be modeled by a binomial distribution. I'll come back to the other piece in a minute. Then the second group did this. Same idea. Those of you in class, you know what we just did. Those that are listening online, you then shuffled really well, drew 10 cards, and counted how many of them were diamonds. Put those 10 cards back in, reshuffled really well, randomly selected 10 more cards, counted how many were diamonds, and recorded that on the frequency table. The second one, the question is this a binomial, geometric, hypergeometric, Poisson, or other? And be able to explain your answer. I'm not going to cover that right now, but we will get to that pretty soon. Then we did this, and we found for those of them that had to shuffle and redraw, there were 14, 20, 14, 13, 10, 3, and after this point, whoever did the rest of these, I don't believe you at all that you did this the right way, because you'll see shortly that this, from a probability model, these are very, 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 very rare. This one is virtually impossible. It's going to be 0.8 zeros and then a 1. So to have 10 cards that you had all diamonds, every card you drew is a diamond, you drew a diamond, you put it back, unless you have a deck that's half diamonds and half something else, or maybe 3/4 diamonds, I'm guessing you did not shuffle well. But this is the issue with theoretical probabilities, is we're left to the fact that it's experimental. Experimental, this is experimental. Experimental means that we have added a layer of error that could happen in this process. So instead of just sampling error, we have human error. You are all humans, you all make mistakes, and someone made a lot of them, is my guess. No judging. Oh, actually, no, I am judging you. All right. I look at data, I assess data, and make decisions on data, which is technically judging. So yes, I'm judging you. I'm going to go back here. So what I want you to do with this is find the average. We'll talk about the standard deviation in a second. Do you remember the formula for the average? It is the sum of each x sub I, times the probability of x sub I. So the relative frequency, in this case, would have been 14 out of, now what's my total? So it's 14 out of 88. This is 20 out of 88. This is 14 out of 88, because it's how many times it happened out of the 88 possibilities we had. So what I need you to do is quickly, in your calculators on a piece of paper, take this number times that, this number times that, this number times that, et cetera, et cetera, et cetera. Add them all up and tell me what this number is. Go. So again, when I said the wrong thing, you were getting a large number like 12. So it's x times its probability, x times its probability. X is 1 times its probability. X is 2 times its probability. X is 3 times its probability. So if you did graph and calculator again, these numbers are in your L1. My apologies. These numbers are in your L2. If you do stat calc, 1 var stats of L, then you do L1, this as your x variable, this as your frequency variable, and you get an x bar value of 2.84 as my experimental probability.
Wow, beautiful.
Which is, now what does that mean? That means that if I were to repeat this process over and over and over again, I would expect on average in every selected group of 10 cards that there would be 2.84 diamonds. So between 2 and 3 diamonds, slightly over 2. Now, when you did that, did you also get a standard deviation?
Yeah.
What is it? 2.54. All right, so s squared is going to be a big square root function that I'm not going to write down right now. But it would involve this same stuff up here. But instead of x, it's going to be x minus mu, or in this case, x bar. X bar was my sample average. So it would be the sum of each x sub I minus x bar squared times its probability divided by n minus 1. These are just formulas that you can look up and find. But this is, again, this is why technology is so useful. It's going to tell me, and what it tells me is, I would expect on average. So again, if I did, this is what it means then, like in actual context. If I were to do this once, and I'd select 10 cards, and I look at how many diamonds are in that, I would expect to be, on average, about 2.54 away from the mean. On average. Sometimes it'll be a little less than that. Sometimes it might be a little more than that. But on average, I'll be within 2.5 of the actual mean. That's what the standard deviation means. It's the average distance of every data point from the mean. But that means if I do it once, I would expect to be no more than, or approximately, on average, about 2.54 away from the mean. So this is the experimental distribution for the sampling with replacement. All right, sampling without replacement, we had these numbers. 6, oh, sorry, this was 6. And then we have 15, 22, 22, 16, 2, 3, 0, 0, 0, 0. And then relative frequency will be 6 over whatever the sum is of that total. This will be 15 over whatever the sum is of that row or that column, which someone's going to give me here in a minute. We'll go with 86. So then procedurally, it would be the same. I would take x times its probability. So if I wanted to, I could actually make a column for that. X times its probability. 0 times 686 is 0. 1 times 1586 is 1586. 2 times 22 is 4486. 3 times 2286, because again, this is 2286 right there. That will also be 4486. follow all those up, add them up at the bottom, and that's going to tell you what the average is, again, for sampling without replacement. So it's sampling without replacement. So now we'll go back and say, can we figure out what kind of distribution this is? Is it a binomial? Everybody shake your head and say out loud the word no. No. Very good. It's not a binomial. Are there two outcomes? Everybody nod and say yes. Yes, it's either a diamond or it's not a diamond. Is there a set number of trials? Nod. Yes, there's 10 trials. Is the probability the same for every trial? No. No, because it's without replacement. I'm taking it out, so if the first card I draw is a diamond, the likelihood of now selecting the second card as a diamond has changed. So it is a yes or no scenario, diamond or not. There's a set number of trials. The probability changes with each one. Are there only two sets that I'm looking at? Yes, of course. I'm looking at diamonds or not diamonds. In which case, this would be considered a hypergeometric distribution. A geometric distribution, if you're wondering, would be I draw a card until I get a diamond, and then I stop. And if I got it on my first trial, my number would be 1. If I got it on the second draw, but I'd have to replace it, though. So a geometric has to be replaced. So a geometric would be I draw a card, look at it, put it back in, shuffle it up, draw another one, look at it, and if that second one's a diamond, then I stop. And my answer would be my first diamond happened on the second draw. That's a geometric. So this then becomes a hypergeometric. Again, only two outcomes, probability changes, set number of trials, and I'm looking to see how many are in it. My set of interest, if you remember that from the slide, my set of interest are diamonds, so there's going to be 13 of those. The set that I'm not interested in, or my other set, so, basically not diamonds, or diamonds complement, is 39. My sample size is going to be 10. And then from that, we would end up using technology to get the rest of this. But this is then the experimental distribution for the number of diamonds in a hypergeometric distribution. Probability distribution function. PDF. I'm going to pause. All right. So then, if you have a computer with you, what I did, there's a lot of places you can go online to find a binomial distribution calculator. I like the ones out of University of Iowa, UIOWA, just like it says right there. All right, but again, what I type into the Google search bar is binomial distribution calculator, and it'll give you a few. This one will give me both my initial information and then the actual distribution. So what you can see is what we had n was 10 because we did a trial of size 10. I had a probability of 0.25 because that was the probability of drawing a diamond. If I leave the X blank, it will actually then just generate this for me, which if I would take that, again, if we could believe it, if we could believe the tally marks from the with replacement group, and if we could take those tallies and rotate this up 90 degrees, you would see that the higher values are on the bottom, just like they are over here, where the most likely outcome is a 2, because it's the highest bar. When we did ours, the most highly likely one that we had was a 1. When we did our experimental, it happened 20 times. The 2 only happened 14 times. So again, experimental can be off, but it's not far off. These, however, are considerably off. We'll actually see that in the table coming up here. Because if you look at 7, 8, 9, and 10, where in class someone said we had 3 of these, 4 of these, 3 of these, and 1 of these. If you look at the bars, they're not even visible. That's how short of a probability bar they are. And what I'd said was, if my probability is lower than 50%, that means I'm expecting more things to happen down here, which makes it a right-skewed distribution. 10 trials. And then if you want to go individually and type in 1, say a 1 right there, it would tell you the actual value. And if I did do that, it would give me this table of values. And then we look at ours. How close were we with ours? We said this was 14 out of 88. What is 14 out of 88 as a decimal? Point what? 159. So we, in our experimental probabilities, found that the likelihood of having 0 diamonds was about 15.9%. Theoretically, it should have only been 5%. Significant difference. Down here, 1, 2, 3, 4, 5, 6 zeros, and then a 9, 5 for getting 10. If I look at just 7 and above, if I were to add all of those up, I am still less than, other way around, I am still less than 1%, theoretically. If I add those up, the probability that x, the sum of the x's is 7 or more is less than, not less than or equal to, is less than 1%. Because if I add up these 4 values, it adds up to not even a percent. It adds up to less than 0.5%. Barely over 0.3% chance. Whereas our experimental occurred 3, 7, 8, 9, 10, 11 times out of 88, which is really ridiculously high. So like I said at the beginning, as I judge whichever group that is, I don't believe they either shuffled well, that's usually what happens, or just got tired of doing it and just threw down numbers, which is known to happen. Okay? All right, so that's the theoretical distribution for the binomial distribution of drawing a card with replacement and counting the number of diamonds in 10 cards. This for 1 second. I'm going to, let's just look at this one. Because you will see for sure NCR, P to the R, Q to the N minus R. You're going to see that formula and need to be able to apply that formula on the exam. So if we do it for 2, we would say this would be equal to 10 choose 2 times 1/4, that was the probability of getting a diamond, squared, times 3/4 to the 8. 8 because it's 10 minus 2. 2 successes, 8 failures. And then this is 10 factorial over 10 minus 2 factorial times 2 factorial. I picked a small number because it's easier. 10 factorial is 10 times 9 times 8 factorial. And there's a reason why I stopped there. In the denominator, 10 minus 2 is 8 factorial, because 10 minus 2 is 8, 8 factorial, times 2 factorial. Well, now I have 8 factorial numerator and denominator. They will reduce to 1. 2 factorial is 2 times 1, so I have 10 times 9 over 2 times 1, so I have 90 over 2, which is 45. What that means is there are 45 different ways that I could draw 10 cards and have exactly 2 diamonds. So it'd be 45 times than the probability of it happening once. If it can happen 45 different ways, and the probability that it happens once is 1/4 squared times 3/4 to the 8th, I multiply that by 45, and that's how that number appears. That's where that comes from. The hypergeometric, we can go hypergeometric. N is the size of the group that I'm interested in. So in this case, this is 13. So in a hypergeometric, if you're going to do it online, this number, the first number, is my group of choice. I want diamonds. There's 13 of them. The capital N is the other ones. There are 39 other ones. M is how big is my group? 10. If I do that, it gives me this distribution. which, again, if I look at the theoretical distribution that we did in class with the frequencies, it follows that pretty closely. Down to 6 for 7. How many? We had none for 7, but it looks like there's a really small probability. Well, we didn't do it that many times, so it's possible I just didn't get one to show up. If we'd run this whole theoretical experiment and everybody did another sample of 20, we'd probably get a 7 or 2 to show up. The more you do it, the more experiments you do, the closer your experimental distribution should look like the theoretical distribution. All right, and that actually has a name. It's called the law of large numbers. If you do something repeatedly with the right same processes, again, using good randomization, my experimental distribution will slowly get closer to my theoretical distribution. The larger and larger my number of trials I do. It's called the law of large numbers. There is not a thing as the law of small numbers, all right, which is actually what casinos bank on. They literally bank on it because they think, well, I'm due for this to happen. No, you're not. When it's random, you're due for nothing, which is why you lose, and they get your money. But you could then individually, like this one here, I hovered over it, and it says for x equals 3, this number is 0.29592. Back, you can actually see at the bottom, it tells you what you'd run it through, and you can find all the probabilities there. And if we... What do we do with the paper? You can keep it. I want my card decks back, please. Thanks, Isaiah. Have a great afternoon. Thank you.
I won't be here on Friday because of the game.
Okay.
Will that class be online? It's gonna be like
Just
that?
like everything else I've done. I mean, you're not going to get everything, but you're going to get quite a bit of what we cover. Yeah.
Is it like gonna be a quiz? Like
Oh, the example problem?
Yeah.
I'll go through that too.
Okay.
Yeah. And I'll record. Oh, yeah. Thank you. Those are non.
And I won't be here Friday because of volleyball.
Okay.
Me, AJ, Miguel, Kobe.
So just make sure someone emails me to
Yep.
remind me Friday morning. It'd be great.
All right.
Thanks.
Hi. Are we able to redo the practice quiz again? Or not?
Yes, you can redo the practice quiz. It's still open. As long as it lets you, keep redoing the practice quiz.
Okay. And also, the question about like.
And it should show you the answers that you wrote and that it was wrong. It won't show you the right answer yet. Keep it.
What's the one where it's like you're 11th in the class, the percentile
Percentile rank, yeah.
I looked up I found the formula for that in the textbook.
Yep.
And I tried doing it and it was still wrong, so I'm not understanding how to do it.
It should just be, so if your rank, it should be rank over total number. Yeah. So if you're 11th, divide by how many people are in the thing.
What's that?
Is that what it is? So then that would tell you your percentile rank. So if you're an 11th person in line,
That's
11 out of however many total, that's your percentile.
Yeah, it's not math.
There's like a formula.
Yep.
Thank you.
Yeah, there might, and this is where some books, I think, make it more complicated. I mean, that's all it really is percentile rank. Every once in a while, I come across, and I'll have to look at our book again to see if they do. Sometimes they'll do your rank minus 1, or your position minus 1, and then divide it by total number of n. But
Okay. If you do like 11 divided by that number,
Yep.
it's
so
bad?
you'd be the 4th percentile. You can't be a higher percentile
4.7.
because you're at 4.6. Well, 5 would be higher, so it'd be 4%. Yeah. So percentile rank is usually only done as whole numbers.
Oh,
I'm
okay,
the 4th
'cause
percentile, I'm the
yeah,
5th
the
percentile.
question says to like round it to the
Oh,
nearest 10th.
well then 4.7.
7? Okay, I put that as wrong. Well,
I'll take a look at that. Shoot me an email reminding me, because I will by the time I get home forget that.
I'll try it again.
Yeah, try it again and see, but yeah. And if I'm wrong, I'll go back and fix that for everybody. Yeah. Yes, sir. Yeah. I tried to make it, because is this going to be likely your last class ever? Yeah. Yeah, so not going to make you go get a graphing calculator unless you already have one. If you have one, use it. If not, just a scientific calculator like this. Something like that.
Yeah, I just wanted to make sure I didn't get like this $97 one.
No, I mean, if you're an engineering major, you should have a calculator that the engineering professors want you to have, that kind of stuff. Because you're gonna be doing a lot more math. For the case for what I do, knowing that we don't have math majors here either, if you were a math major, I'd be like, absolutely invest in this because you're gonna use it a whole ton. So for me, if this is it for you, just a scientific calculator, you don't need this.
Yeah, no, I just wanted to make sure I was like prepared for the tests and
Yep,
exams and stuff.
yep, I will make it so that as long as you have a scientific calculator, you can get through it all. Yeah, I don't want to tell you all my little tricks that I do to get there to allow you to get past certain things, but yeah,
All right, thank you.
you're welcome. Which is also why I use a free book online. We can get all the way there without having to go buy a $130 textbook. All right. Hello, did you write the words about bring your own, leave the markers here?
Yeah, I actually.
I
brought my
always
own.
bring my own because I can
Yes.
never trust.
Right here.
Yeah. Yep. And I bring my own bag. I don't like those erasers because they leave smears.
Oh, you're right.
So I just have
I have my own too.
rags from at home.
Yes.
Works so much better.
It's better. It
Yes.
does look nicer,
Yeah.
actually.
Yep.
Oh, that's good. It's good tips and tricks.
Yes.
I'm sorry.
Yeah, I'm just trying to get out of the
Yeah,
way
yeah,
here.
you're good. You're totally good. I don't want to push you out of the way. I just.
Well, I also tend to, is that law of entropy? You tend to consume all the space that you're in.
Yes.
In chemistry, is that entropy or enthalpy? Anybody know?
I don't know, but it makes sense why people do that.
Yeah.
Use up all the space that they're in.
It's also true with time. Work expands to fill the time available.
Well, yes, exactly. Yep. Alright, this. And. Not Doctor. Thank you. Appreciate it every time. Yeah. New.